All right. The very first course I was ever teaching in university, I showed up. I told everybody, welcome to CS 101. And that was enough. I realized people are looking at each other, and half of people started to leave. And I was like, these guys don't even know what course they're taking. But it was me who was in the wrong room. This room kind of reminded me of the same story from 6 years back. All right, thanks for coming, everyone. We will be talking a lot about LLMs. And wait, aren't we doing enough of that already? Do you want to hear more? So I have done a bunch of different LLM talks over the last kind of 2 or 3 years, but this is a brand new talk that I brought to this conference. I was working on this on the flight. It was a long flight. And yesterday, last night, this morning, so I hope you like it. But we are not going to talk about, I mean, on a different day, I can tell you how we can change the world by just a couple of lines of code, building this fancy agent. We can do that on a different day, not today. Today I want to give you a 5-part story about LLMs. So technically we're going to talk about the beautiful, the ugly, I mean, mostly the ugly. But yeah, so a little bit about myself. So my name is Ryan Rad. I have been in AI for a little bit over 15 years now. Across different sectors, I get bored pretty easily. So in industry, I've worked as a machine learning engineer, research scientist, software developer, team lead, and AI advisor last kind of 6-7 years. In academia, beside teaching, I would say 45, I was counting this morning, 45 courses over the past 6 years across 5 different universities, research in AI, and I have also helped some top universities build master's program or a specialization pathway, and also just last year, the first ever formal generative AI, master level generative AI course in North America. If you're wondering what I was doing during my weekends last kind of 2 years, I'm actually working on a book that I'm hoping going to come out in January about LLMs and agentic AI. Okay. Oh yeah, and I'm from Vancouver, Canada. It's my first time in Sweden and first time in Øredev. It's such a beautiful place and such a great conference, by the way. For those of you who haven't been, Vancouver is such an amazing city as well. There is one thing cool about Vancouver is that we experience everything, after everyone else in the whole world. So it's going to be New Year soon, and everybody will be doing fireworks. We watch them on TV, and everyone is like, "Oh, I can't believe it's 2026 already." And I'm like, "Yeah, because it's not. We still have 24 hours to go, and that's a lot, right? You can do a lot in 24 hours." All right, so 5 parts, right? So this is part 1. So we all use LLMs, and we have this very interesting, complicated relationship with them. We love them for a moment, and then we hate them the next moment. We love them because they feel sometimes lifesaver, like so genius, because they actually are. And just a moment later, they seem so dumb and stupid, because they actually are. But we still use them, right? And we still love them. So for example, if I wouldn't use Gemini for this photo, I would have had this slide. Well, I even use Gemini to tell you what it would look like if I don't use Gemini for this slide. But you see my point, right? So I'm not sure if you have ever looked at a reasoning loop of your favorite LLMs. So a few weeks ago, when I was designing a brand new homeworks for my computer vision course, So what I do nowadays is I just run my homeworks by all my favorite LLMs first before giving it to my student. And then there was this very stupid problem that we got stuck on, and I was wondering why this is happening. So I was looking at the thought process of one of my favorite LLMs and see what we got. The user is frustrated. I should follow professional protocol. Good. I have checked the code many times. Everything is perfect. The logic is flawless. But the depth map is reversed. So this is talking about depth map, like technically, in computer vision. The second paragraph. The user said it should be inverted, but it's not. Or wait. It is inverted, but it shouldn't be? I inverted the inversion? And the last paragraph. The user is right to be frustrated. So reasonable, right? We are all frustrated. Maybe if I just check the code again, it's still perfect, still backwards. The near things are far, the far things are near. I'm experiencing something human call existential dread. Like, seriously, what did we do to them? I really feel bad a lot of times for LLMs. So that brings me to my last slide for part one, which is I always think LLMs are, if not the most, one of the most over-engineered software product of all times, with all the complicated layers to make sure they output something useful, something interesting. Okay, part two, the accidental discovery. So I want to backtrack for a little bit. So language models have been around for a very, very long time, right? I think if you remember the first smartphone you had, probably had this autocomplete feature. And that was technically a language model, not a large one. And then what happened was, so a little bit about from machine learning. So what you're looking at is the objective of an entire 2 hours session in my machine learning course. So we used to talk about in machine learning for quite some time about how important it is for the complexity of your model to match the complexity of your data and your task, right? That has been such an important topic in machine learning. And we came up with all these different optimization techniques over the years to train the best model for the amount of data that we have available. So there is one thing in this graph that I'm not actually showing, and that's the assumption. So before 2020, whatever computational problem you're solving, you have limited amount of data. It doesn't matter how much, maybe a few hundreds, maybe a few thousand, maybe a few hundreds of thousands, but limited amount of data. You don't have 10 trillions of data, right? Okay, so we would always, like in machine learning research, we would always say, oh, whatever problem you're running into, if you can get more data, do that first, right? And if you can't get more data, then let's do augmentation, let's do dropout, let's do all these different optimization techniques that we came out over the course of 15 years. Or maybe from the first time that gradient descent was born, 1989, by Jeffrey Hinton. So that was the assumption, right? So what happened in 2000? Okay, so if you don't, let me also tell you for a second, if you don't follow, if your model doesn't match the complexity of your task, what's going to happen? Some of the things that you're seeing on the corner of the screen right now, this model will become very, very unreliable. They give you results that are way over range and so on and so forth. Okay, so here's the interesting part. So around the time of 2015, a few people wanted to really test this hypothesis, right? I'm talking about the law of scale, right? So we always knew that if you have more data, you probably can train better models, right? this paper that I'm sharing with you right now actually came out 2021 by DeepMind, Google. But in 2015, it was a big deal. If you want to invest millions of dollars training a gigantic model just to test a hypothesis, that would require a lot of courage. So a few companies did that, right? A few people did that. And it's very interesting. If you look at this paper, I'm going to save you a lot of time by just telling you everything in 2 sentences. So it turns out you can model the accuracy of the performance of LLMs by just 2 parameters, just 2 things. So if you know how much data you have, and if you know how many parameters, how large, or how complex your model is, you can, by a very good accuracy, predict what you're going to get out of this model. That's phenomenal, right? And so in 2015, or a little bit maybe after that, people started to think, how can we test this? Where can we get a lot of data? And you guessed it, text, right? Why text is a great test bed for the law of scale? Because they are free, and they do not require annotation. You just mask the next word in any text document, that will be a training pair for you already. You don't need to go through all this expensive human labeling and annotation for text, right? And where do we get that? Internet. So that's how large language models were born. They were not, we weren't planning to, we weren't thinking in 2015, what's the next thing the world need? And LLMs. We were just thinking, people were just thinking, what would be a good test bed to make this, to put this into the test? And then text was obviously. The process of creating a functional LLM, the first phase is, we already described, so you technically grab the entire internet, or as much as you can handle, and then you throw in thousands of GPUs and a few millions of dollars at least to get a model that can do what? We're going to call this foundation model, and you're going to do it probably only once a year or so. And this model will just predict the next word for you in whatever text document, right? So this was a very important moment in the history of LLMs in 2022 when OpenAI published this paper. This is where they actually introduced the idea of instruct tuning, which was huge, that you can control the behavior of these next word predictors by training them and fine-tuning them in a very specialized way. And that gave us a stage 2 to make these models do something useful. For example, hold a conversation, answer a question, or so on and so forth. And we call this instruct model or fine-tune models, right? Fine-tune model or instruct model versus foundation models. After that, between 2020, since then, to 2024, I would say, people were very busy coming up with techniques that can put these LLMs into doing something useful for the for the community, right? The 4 techniques that came out was prompt engineering. Okay, wait, these models are so fluent, but it's hard to talk to them. That's a contradiction in itself. These models cannot understand factual information from non-factual one. Let's do RAG. And so on and so forth, right? RLHF, these models are not aligned with human preferences. Let's do RLHF. And of course, if you need further fine-tuning, you can always do that, right? So 4 techniques was born to kind of bring LLMs into life, and pretty much 99% of applications we are seeing today are the result of a combination of these 4 techniques. Okay, so the ugly, the issues. So I want to talk about. So I don't want to talk about the problem of counting R's in a strawberry, right? Which took us a good 2 years to get it right. But I want to talk about fundamental issues that's going to reveal the next step in this domain. All the problem, I would say, I think at least the first 3 are original. I never shared them anywhere. And here's the thing. Well, if you know how they work, you can come up with thousands of examples every day. to make them fail. And but I'm going to start with, yeah, I think this is another thing I don't want to talk about, right? Prompt injection. You could buy from Chevrolet. I'll let you read it. You could buy a Chevy Tahoe for $1. It's too late now. You can't. Sorry, but you could in 2024. So I don't want to talk about this, right? Original problem. So a little bit. Why not talking a little bit about understanding physics? So this is what I did just a couple of months ago, and you can read it. Assuming the direction of gravity is reversed by 360 degrees, when an apple falls out of a tree, which direction will it fall in? And look at the reasoning. It took, I'm pretty sure it took 12 seconds or so. And here is the main part. It would fall upward. I'm not sure about you, but Isaac Newton wouldn't be happy about this. Let me show you another thing. How many of you are familiar with this illusion? Okay, few people. Good, good. So those of you who are familiar, you know that these orange circles are exactly the same size, right? Those of you who haven't seen this, it would be kind of hard. But if you don't trust me, I hope this helps. They're exactly the same size, right? Okay. Here is my version. Okay. Now, I'm going to ask my favorite LLM. What do you see here? And look at the response. These are two interesting visual illusions known as Ebbinghaus illusion. Oh, perfect. Very nice. But wait. In both images, the orange circle in the corner are actually the same size, but they appear different due to the context of the visual context of the surrounding area. Let me show you another one. How many of you have seen this before? A few more people. Huh? Amazing. Yeah, I think more than half of people. So the Zoner illusion is also pretty interesting. Blows my mind every time. But the question is whether these white lines are parallel, yes or no, right? So they are. I created a different version of this. And they are not parallel anymore. By the way, these are generated last week. So these are not like a year ago or 6 months ago or anything. So are these 4 lines parallel? It took 11 seconds of reasoning. And it says, yes, these 4 lines are parallel, although they may not seem so. Again, very reasonable, very fluent, very confident. Let me show you a few more things. These are not original, but I'm not sure if you have heard of this, but these are fundamental limitations. The reversal curse. So this is a paper that came out a little bit less than 2 years ago. If you ask an LLM, who is Tom Cruise's mother, you will get a perfect response, right? Because they have gone through Tom Cruise's bio. Now, if you ask the same LLM 1 second later, who is Mary Lee Pfeiffer's son, it will tell you something like, as of September, my training data is not up to date, so I'm unable to answer this question. So this is called the reversal curse. So when again, so there are a lot of people talking about we are running out of data. Show them this example. And we're going to talk about that again later as well. So another problem I want to highlight, this is my last problem for part 2, is constant flat latency. So if you ask any LLM, what is the capital of Sweden? And also ask about quantum computing. It will take the exact same time, energy, and resources to answer these 2 questions, which obviously doesn't make sense and it shouldn't be this way. These are some of the fundamental problems to show some limitation, inherent limitation of LLMs with all the progress we have made over the years, right? And that brings us to part 4. So we're going to talk about those fixes that we made and how that changes. Changed already. So the cascade of fixes that failed. That's part 4. I'm going to start, by the way, about talking a fundamental limitation. Why do LLMs hallucinate? The answer to this question is obviously, sometimes I feel like it's obvious, but it's not, maybe. So a part of the problem is they are forced to predict. So technically, deep down, if you really look at a foundation LLM model, it's doing a multi-class classification. The only difference is we have thousands different classes. So this is not a binary classification. It's a multi-class classification with few thousands of labels. So what happened as a result of that is the model, so technically we always compare a multi-class classification model with a random guess as our baseline, right? Why? Because you can always randomly guess, and there is always a chance you will be right. If you have, for example, 4 classes, you always stand 25% chance getting it right. Like that's just probability, right? So these models are smart, deep down. They know that. So there is no reward for being quiet. There is no reward for saying, I don't know. There is no reward for shutting up. They have to generate the next token because whenever they do that, there is a little bit of positive chance they get it right. If they don't, they're going to fail anyway, right? And the other thing is they reward for plausibility, not accuracy. I'm not going to open this up based on the time we have here, but fluency is very different from understanding, right? So they're very fluent because they are rewarded for plausibility. And that's a very small subset of the whole word, right? The factual word is a completely different word than the plausible word. Okay, fixes, sorry. We are talking about fixes. So I'm going to start with reinforcement learning because a lot of people love reinforcement learning. And they think it's such an amazing, smart idea, and we owe everything we have right now about LLMs to reinforcement learning. That's one side of the story. The other side of the story is that reinforcement learning is actually terrible. So I'm showing you an example. So usually, let's say you want to solve a mathematical problem or a problem from physics or chemistry. So normally it takes a lot of trials, right? We get it wrong many times. And then based on those attempts, we start to find a path to the final solution. And then eventually it takes some time, maybe a few days, maybe a few weeks, but we might get it right. So when you get it right, that's one example. That's going to give us the label. And now, whatever we have done to get there will be upvoted. So technically, all those mistakes, all those terrible ideas that we implemented first, until we learned, maybe only the last 2 part was useful, but everything gets upvoted. So this is such a noisy, garbage way of collecting feedback. How human does it? Quite different, though. So a lot of people think reinforcement learning is exactly how human learns, right? That's how a newborn baby learns how to interact with the environment around them. But is it? So a human, when we are solving a computational problem, we start from somewhere, right? We make a lot of mistakes. We end up solving it. And then we look back, we reflect. We look at, okay, what caused us, what took us too long to get to the final solution? We realize that, there was this fundamentally wrong assumption that we had initially, and that actually got us to to a completely wrong path to get to the final answer. This is not how reinforcement learning learns. Okay, to fix this, what did we do? I'm going to start the next part with, a wise person once said, all models are wrong, but some are useful. And a lot of times we forget about, again, backing to principles. I think the state of LLMs right now, we need to get the principles right. So the way to solve reinforcement learning was, it's very hard to get, by the way, human feedback, right? So I think a lot of LLM models were initially voluntarily, were asking for user feedback. Okay, out of these two responses, which one do you like better? Can you rate it for us? But you can't scale that, and a lot of people don't do that, right? So it was very hard, and we got, a quick fix. Okay, can we do it semi-automatically? How so? We have some labels from human feedback. We train a reward model. This is exactly how we have been doing RLHF over the past 2 years. We train a reward model based on human feedback. We are trying to mimic human feedback by some data. And then we forget about human, and we just use the reward model, learn from it, hoping that it's going to align with human at the end of the day. Okay, what happens? Well, there's a problem with that. So LLMs are silently collapsed. I think this is a concept that there are a few papers. This is one of those that I highly recommend if you're interested. But they show that, although these models are collapsed originally, when you use synthetic data by larger models, whatever other models, you iteratively fit that synthetic data to the same model, their distribution gets narrower and narrower. And you ended up with having a collapsed model that is not good for anything. Maybe this wasn't helpful. Let me show you 2 examples. Number one, from the same paper. So they show, this is the MNIST data set. And you can see, if you use synthetic data, what you're going to end up getting. It's all zeros. All digits look pretty much the same. So they think 8 is actually 0, right? They collapse. And if you don't like this example, I'm going to show you something that you're already familiar with. And I showed this before. Okay, let's do this. Let's say this is my reference model. And this is exactly what I did yesterday for this talk. So I used this prompt and create a version that looks like it was drawn by a 3-year-old with very basic shapes and colors. And you know what I got? I was like, okay, so the only difference is emojis, maybe, less emojis. And I was like, okay, this is not helping. Let me see what I can get. If I change my prompt to a 6-month-old. So create a version that looks like it was drawn by a 6-month-old. And this is what I got. I would say pretty impressive for a 6-month-old. This is model collapse. So I really don't know any better way in the whole world to tell you what is model collapse. So the model has only 2 ideas about how the people might possibly draw that original image. You can use the same strategy with jokes. Ask your favorite LLMs to come up with 3 jokes. Then ask for more jokes. They don't know. This is what we call model collapse, right? They're silently collapsed because it's not obvious, but if you dig a little bit deeper, it will become obvious. Okay, how are we doing in time? Okay, that brings us to, I think very soon I'm going to do the last part. Hopefully we're going to have a couple of minutes for questions as well. Okay, what else did we do? This is an interesting one. We made the model bigger. Bigger model are better, right? So over the last 2 years, most of the models, almost all of the models we are actually using on a daily basis contain 500 billion or more. So between 500 billion to 1 and 1.5 trillion parameters. Why it doesn't help? So we are making the same mistake we were making with machine learning 20 years ago, 15 years ago. We are running out of data. So we don't have new data to use for these models. We are making the models bigger. And it's very interesting. I would highly recommend, I don't have it here for this talk, but if you give a super tiny LLM, well, say 100 million parameter, a sequence of thousands random words, it should be illegal if anyone can remember that, because it's all noise. So give 100 or 1,000 random words to this LLM, and that LLM will remember that for you. And that's not learning. That's very obvious memorization. And that is what happens when you increase the capacity of your model, and it gets super easy for them just to memorize the stuff rather than really. Why would you even bother to understand if you have all the memory in a whole word? Okay, part 5, what's next? So I'm going to summarize everything we have done in 3 acts of our tragedy. So part 1, 2022-2025. So the mantra here was, bigger is better, just a scale. And that's exactly what you see from the trends. We are just training bigger and bigger models. The theme is, we are drunk on a scale. In engineering, we have a principle. If something is working, you don't change it. Why would you? It's working, so let's do it. Let's keep doing it. Something interesting happened sometimes around last year. So that's the consequences of that, right? Just bigger model, more expensive every day. So we started building models that would cost $1 million and $2 million, and people would call that expensive. And that definition of expensive is changing every day. And so what happened last year? AI companies understood that it's very hard. I'm talking about frontier labs. It's very hard to make money. We are losing money, right? That's not what they tell investors, but yeah. So this is the economist hangover. 2024 we are still in the midst of this period. 2024, 2026, we suddenly see a lot of interest. This is the research that I was doing since 2021. And suddenly a lot of people are doing efficient LLM training. Interesting. So the problem was these models actually would cost a fortune to run. And the companies have to find a way to lower the cost. And we had a lot of interesting innovation in this period. So we have things like a speculative sampling, a mixture of experts. We have lots of different techniques for quantization, lots of different techniques for knowledge distillation. And these are beautiful engineering breakthroughs. Don't get me wrong. So let me actually show you one of these. How many of you actually know what is a speculative sampling? Okay, 2 people, one person, great. So it's going to be new to a lot of you then, I would say. So let me spend a minute here. So a speculative sampling work technically on the principle of bringing the cost down. You remember the problem of flat latency? The capital of Sweden versus quantum computing? This is kind of to handle that, right? So you have a small model. This is a tiny LLM. And this tiny LLM will generate 5 words for you at the time. So this is how it works. We're going to call this assistant or draft model. It gives you the first 5 words. And then we're going to call our main model only once after 5 words. And we're going to just do a forward pass to get approval, to seek for approval. And this gigantic model will do that and tell us, I 100% agree with the first 3 tokens. The first one, not really sure there. I would say autonomously. And the way this works is, okay, whatever that comes after that rejected word will be discarded. And we're going to start over with the first 4 words. And we're going to keep doing this. So what happens is you can get like 3 to 5 times efficiency, theoretically. In practice, 2 to 3 times. But there's a lot of problems with these techniques that I don't want to go. I don't want to ruin the party, right? It's pretty nice. Let me end there. But actually, what we were doing is we were ignoring the fundamental problems in LLMs. We were just trying to run the same flawed architectures cheaper. Okay, that brings us to, yeah, so the theme for the second part was, we can't afford to keep doing this. Let's make it cheaper. And the third part is something I would prefer to call sober rebuild. So I think there are very few people right now talking about this. Obviously, Jan LeCun, Andre Karpathy, Fei-Fei Li. There are a few pioneers of AI that are actually talking about things, some of the things that I'm going to put on this box. But these are very, very few people compared to the overall effort in this space. So reflect. Act 1 was driven by hype. Act 2 was driven by economics. Act 3 has to be driven by understanding. So how many people here think transformers were this magical invention? Transformer is all you need. Well, they weren't. So if you look at the transformer, there are many components that actually contribute to the success of them that is coming from the machine learning research prior to transformers. Like what? Okay, we're still doing gradient descent. We are still doing residual connection that came out in 2015 by ResNet. We are doing encoder-decoder architecture, which was first introduced in 2014. Right? And so on and so forth. Even self-attention was not new. So attention was not new, but self-attention and multi-head attention were a new invention. Right? So, and then obviously the main thing was positional encoding and the parallel processing. Those were the new component, but it wasn't entirely new. That's my point. So what we're really going to see is there is still going to be no magical fix. We need improvement everywhere. We need better algorithms, better than reinforcement learning. We need better architecture. So Google somebody just came up a few weeks ago with this sparse attention. I haven't read the paper, but I just read the abstract. That's one architectural innovation. Framework. We need to do better than autoregressive. Jan LeCun says, these LLMs should not be called LLMs. These are not a generic LLM. These are autoregressive LLMs. Why everybody calls them LLM? Beyond autoregressive, because autoregressive will impose very, very important limitation. Data. I think we need better data. The average data on the internet is garbage. And it's very amazing, actually, very impressive how these models are learning from those documents. So the theme here is reinventing the foundation, start building differently. Thank you so much, everyone, for being here. I think I can take one question maybe, but I promise I will be on the speaker corner after the talk. Oh, yes, please.
Is this problem somehow that we are running into this sort of same thing again and again? Is it somehow inherent to human nature and this topic of machine learning or AI? Do you think the next models will have the same issue that we will try to scale them up and run into economic constraints and then we sort of tolerate some kind of bubble or AI winter?
Very good question. So, history repeats itself, right? So over and over and over again. I guess part of the problem. So the answer is yes. We are just seeing all the core mistakes happening again and again. But I would say a part of the problem is when you get the attention of the entire world. So previously AI companies just have to convince investors. Now they have to convince the entire world that they are better. So there is so much pressure on AI companies to improve tomorrow. and with all the failures that go viral. So there is just so much pressure, I think, that they're focusing, I mean, a lot of them are focusing on short-term gain versus the long-term win. That's the best I can do for that question. Yes, please. Very good question. So I think we're heading there for a bunch of different reasons. One is the economy efficiency. For example, I have done research in that area for environmental sustainable, for a completely different reason. A lot of people are doing research on that area for efficiency of it, but I really think we should be doing research on that area for getting things right. So the example we were talking about, these LLMs having a gigantic memory. So that's the problem, right? So we need to get the core cognitive correct, right? So I love playing with the small LLMs because they have to me, small LLMs are more impressive than the large ones with what they can do, right? And a lot of times they don't have the answer. A lot of time they haven't memorized so much stuff, but we really have to isolate these two things. We need to get the core cognitive right rather than getting the memory component. Right, so those are the three reasons why people are going for small LLMs. But I really hope we will see more of the third group, people who are doing that for understanding and for improving the capability of the model. Yes. Yeah, very good question. So there are a few things I can say about that. I actually have a slide for it. That doesn't show up. Okay. A few things about we are running out of data. So number one is if you keep feeding synthetic data that is generated by other models to your model, what's going to happen is each model has learned its own distribution of the word, and it's very limited. There are lots of cracks in these models, and starting with that. So if you start with the whole internet, you see what we get. Now, if you start with that model, you're just going to get something that is less useful over the time. So a lot of people do that for very specific problems. Synthetic data used to solve very specific, bridge very specific gaps in the data, but overall they can never be a solution. However, we don't need to. I personally think we don't need to be worried about that. So people who are worried about we are running out of data. I have this 3 notes. Number one, there is an assumption here is that we used up all the data, which is completely wrong. Let me tell you a very simple analogy that is, I think, surprisingly helpful. We read the same book, and we learn new stuff every time. So that doesn't mean we used up all the book, right? And a model collapse showed that we have not been learning from the data enough. So there's so much potential in the data. And also the other assumption is that we already got the algorithm, the architectural component perfectly, which we haven't. Yeah, I think we're running out of time. So this was a wonderful conversation. I promised to be on the speaker corner for a while. I would love to continue this conversation with you. Thank you.